Welcome back, brothers and sisters. This is 155 min stack. This one's not too bad. But it's a little bit tricky. I wouldn't say it's easy, but it's definitely a little bit tricky. But let's read the problem. Oh wait, first time doing this problem, by the way. Don't look at that. Design a stack that supports push, pop, top, and retrieving the minimum element in constant time, right? So the key element here being in constant time, that's what kind of makes this a little bit tricky, right? So if you don't know what a stack is, we're going to go over it just real quickly. So a stack is a LIFO object or data structure, which means last in, first out. So you want to imagine like a stack of plates. You're washing at next to the dishwasher or next to the sink, and you add whoever's adding the plates, right? So you're gonna do the dish, right? That was the most recently added, right? It's not like a queue, right? Where a queue is more like a line at Starbucks, right? People are queued from the front and people enter from the back, right? So push pushes element X onto the stack. Pop removes the element on top of the stack. So it's like taking the plate off the top of the stack of plates. Push is like putting a plate on top of the stack of plates. Top is just getting the top element, so we're not removing it at all. You want to imagine top is just like looking at the top of the plate, right? Looking at the plate on top of the stack. And get min is retrieve the minimum element in the stack. So this is why this is called minimum stack. So the key being here that the smallest element in the stack should be retrievable in constant time, right? And so this is the problem. So a naive approach, right? So I think walking through the algorithms that don't work is going to help you see why this algorithm does work. So you can actually go with a fairly naive answer here, and it works. It works, but you don't get constant time removal. I mean, constant time of getting the minimum element, right? So imagine this. You push an element onto the stack. Right? You push an element onto the stack, right? Every time you push an element onto the stack, you record the minimum element, right? Is this element the smallest element we've ever seen, right? And as we keep adding elements, as you keep pushing elements onto the stack, we'll keep a running, I guess, minimum value, right? Of what was the smallest element that we've seen thus far, right? And that will work if you say get min, right? You'll get the minimum value at that time, right? But as soon as you pop an element from the top of the stack, right? And if that element happens to be the minimum value, that's where that solution falls apart, right? Because if you pop the element on top of the stack and it happens to be the minimum element in the stack, right? What you realize is you have no idea what the next minimum element is, right? The only option left is to linearly search through the rest of the underlying data structure that you're using to implement this to find the minimum element, right? And so what you get here is push, pop, top being constant time and get min being linear time, which kind of sucks, right? Kind of sucks. So what underlying data structure should we use to represent this, right? So you want to think about, right, push, pop, and top have to be constant time, right? So the easiest way to represent this is with an array, right? And with an array, you get push, pop, and top are going to be constant time in pretty much any language, right? Because if you think about an array is just, memory, contiguously allocated memory, right? And so the idea with an array is that you have a bunch of, the same sized elements, right? Allocated in some arrangement of, contiguous blocks, right? And so if you want to get the sixth element, what you can do is multiply 6 because you want to get the sixth element multiplied by the base size of the block, right? So you can instantly go to the memory location where the value that you're searching for is, right? And so with an array, you get constant time adding an element to the end of an array, assuming there's space for it, right? Because if you know the length of your array, let's just say 10, you can do length minus 1, which is 9, times the block size, and you'll instantly get the memory address for where that element is stored. So then you can just store the element there. Same thing with pop. It's just the same thing as adding to the end of an array. Will just be removing an element from the end, right? So you want to imagine this as like a line, right? If you're imagining a line at, let's just say, like a pizzeria, anyone can join at the end, right? They won't disturb anyone else in the line. However, if you have someone who inserts themselves right in the middle of the line, right? What you end up having is, if you insert yourself in the middle, everyone who was behind where you're being inserted has to kind of shift back a few steps. And this shift back a few steps is going to be a domino effect throughout the entire line. This effect is amplified even more if someone cuts right at the front of the line. So if someone's just about to order and someone cuts right in front, right then and there, everyone behind the first person has to take a few steps back, right? It's just how, space works. So how do we solve this problem? So what I'm leading you to here is that we're going to use an array, right, to represent the underlying data structure here, right? Because we get a lot of the basic elements of what a stack needs for free, right? We just have to implement some custom logic to make sure that getting the minimum element is constant time. So let's start with that. So self.stack will be equal to an array. So this will be our stack that we're represented with, right? So how do we make sure that get min is constant time, right? So I kind of alluded to it earlier, right? If you were to keep in the previous example, in the naive version, if you kept just a simple variable called self.minimum value, right, and you just set it to, let's just say, math.infinity, right? And so what you would do is you would just, as you add elements to the array, you would say, hey, if x is less than self.min value, oops, that's not Python. If x is less than self.min value, then self.min value equals x, right? And so you could naively go with this, and you would be right up until you popped an element, right? Like we said, if the element that you popped was the minimum value, how do you get the next minimum value, right? And so what's cool is that when you're doing this part right here, you're actually overriding the previous minimum value, right? Because assuming that you're adding multiple elements to the stack, which you should be, right? You'd be overriding the previous value, right? So self.min would ideally start at like a math.infinity, just so you can take the minimum of any value that is added to the stack, and you would take the minimum, right? So the simple answer here is that the naive version works, right up until you pop the element on the stack, right? But what if, instead of keeping one value, you just kept another array, right? So in this idea, right, in this concept, you basically just keep two parallel stacks or arrays, right? Well, two parallel arrays. So the first one, self.stack, is just going to keep all the values in the stack, right, added, added in from the top, right? And minimum value would do the same. So every time we add an element to the stack, we'll keep a record of the previous local minimum for every item below it, right? And this works because you have to think about how a stack works, right? When you're operating with a stack, all of the operations that you can work with happen at the end, right? So you can't modify anything at the very first spot or in between without having to remove everything from the top and getting to that point, right? Just like if you had a stack of glass dishes, you can't pull a dish out of the middle, right? It's just not how the stack of dishes works. If you pull one out the middle, they all kind of break, right? And besides the example, you kind of get what I'm saying. So you can only really take dishes down from the top, right? You can never really take a dish down from the bottom because they'd fall over. So that being the case, what I'm really saying is that items below a certain value are fixed in place, right? Until you pop that item off the stack. And what that means is that if every time we add an element from the top, what you'll see is that we can take the local minimum at that time, right? So for example, if we have 1 in the stack so far, right? So the minimum value when we add it, because there's no elements in either array, it's just going to be 1, right? So the first item in the stack is 1, and the minimum value for the stack right now is 1. That's constant time. We can just take the last element in the array. Now, well, let's add 3. Well, 1 is too good. Let's start with 5, right? So 5 is the minimum value when there's one item in the stack, right? Or in the array. So now let's add 3. So we add 3 to the stack, right? And we say, hey, which one's smaller, right? So we want to allocate a spot here for the minimum value, right, at the time of adding 3, right? So which is smaller, the minimum value right before this or the number we're adding? Well, 3 is, right? And then we can add 1, right? And then we'll say, hey, what's the minimum value we've seen so far? Is it either 3 or is it the new number we're adding, which is 1, right? And we'll say, obviously, it's 1, right? And so now we want to add like 7 or something, right? And so the minimum value, right, at the time of us adding 7 is just going to be 1, right? And this is true because at each time we add something into the stack, we're kind of it's kind of like a chain of command, right? So 5, when we added 5, right, it was the smallest in the list. But when we added 3, 5 was the smallest in the list. So now 3 is the smallest in the list. And when we added 1, 3 was the smallest, but 1 is smaller than 3. So now 1 is the smallest in the list, right? And so this is how this kind of works. And so we can implement a very simple version here. And so what you have is just 2 parallel arrays, one storing the actual elements in the array and one storing the minimum values at the time of addition for that value. So what we'll do is we'll say, when we're adding an element to the stack, the first time we add, right, you have to make sure that self.stack, if it's empty, right, our adding to it is going to look a little bit different the first time, right? Because like we said, when we're adding an element to the stack, right, it's the first element, right? What are we taking the minimum of here, right? 5 is the only element in the array, so 5 has to be the smallest element in the stack. So when the stack is empty and we're adding an element, we're going to say self.stack.append x self.min value.append x, right? So that would make this scenario correct, right? There's no elements in the stack, let's add 5, and there's no elements in the stack, so 5 must be the smallest value, right? Now every point after that though, so we're going to return here, or we'll just say else, I guess. So anytime that's not the case, right, so once we've added more than one element, we'll say, hey, self.stack.append x, right? That's always going to be the same. We're always going to add an element to the stack, right? But how do we take the minimum value, right? And like we said, if we have 5 already in the array, right, we want to add 3, well, like we said, we're always going to add the element to the stack, right? So that's what we're doing on line 15. So what's the minimum value, right? The minimum value at the time of adding 3 is going to be 3. Well, why is that? Because it's less than the last minimum value, right? The last local minimum, which is 5. So what you see here is that we're doing kind of a min of self.min underscore value sub -1, which is going to be the last element in the array, and the minimum of that and the number we're adding, right? And that's what you get. Right? So when we're removing an element, right, and we're popping an element off the top, right, it's going to be very simple, right? Other than the case, right, where you have self.stack is equal to 0. So this the length of the stack is empty. We're just going to return none, right, because there's nothing to remove. Other than that, though, if we want to remove an element, we're just going to say self.stack.pop, right? But like we said, imagine here, right, we want to pop the last element we added off the stack. It's 3. So we popped the top off the stack already, which is the array representing the elements that we're adding to the stack, right? Well, what's wrong here, right? If we were to say get min now, right, we'd return 3. But 3 is not the minimum. 5 is, right? So what you need, right, is a parallel removal of elements. So we're going to say self.min.value.pop. So remove that element, right? And when we want to do top, right, top is just looking at the last element in the array. We're not removing it or anything. We just want to look at it, right? So we're going to do another check here, right? If the stack is empty, right? If the stack is empty, then there's nothing to look at on top, right? We're just going to return 0. Otherwise, though, we're just going to return self.stack sub -1, right? Just return the last element in the stack. Now, this was what was kind of really cool because it makes get min really, really simple, just as simple as the other ones. So if the stack is empty, right, and because we have a pairwise removal of elements, right, whenever we remove an element from the stack, we also remove its minimum value. So if the stack is empty, it means the minimum value is empty. So if the stack is empty, then we're just going to return none. Otherwise, right, all we have to do is just return the last value in min value, right, which is going to represent the stack. And so our answer is wrong, as you can see, because I put 5 in the list when I shouldn't have. And there you go. So that is the answer, right? And so there's actually another way you can do this, right? Now that we know that these can be represented with 2 stacks, right? What you can do, right, is you can make it even simpler. Well, what if we just use one array, right? So we'll just use one array and we'll call it stack, right? And so just to mirror it with the example we had before, but what if we just did the same thing except with a list of lists or a list of tuples, right? So what's the difference between this? So each element, right, when we kind of it's going to simplify the implementation a little bit, but each time, right, we add an element to the stack, we'll add the minimum value in it as a tuple, right? And so if we add 3, then 3 will be the minimum value at the time, right? And if we add, let's just say 6, right, we add 6, well, which one's smaller? The new value that we're adding or the last value? The last minimum value that we said was for the previous element we added. Clearly the last value, right? And so in this way, even with the method where you have 2 different stacks or you represent it as one list, you get this kind of chain of authentication, I guess, where, you know, each value you add kind of reinforces the idea of which value is the minimum, right? So we can do that version of the implementation here. So we're just going to use one array here, and when we're adding an element to the stack, right, how does this change? Well, it's only one thing now, right? So what we can do is just say x comma x, right? And so in this version, right, we have 2 different lines, right? Self.stack.append x and the minimum value of the last the parallel stack with the minimum values that we had, or the new value we're adding, right? So this is going to stay very similar as well. We're going to say x and the minimum, right? And just to copy this, I feel like it'll make more sense. We said we'll take the minimum of the last value we added to the stack, representing the minimum value for that element previously, right? Or the new value that we're adding. Well, min value is gone, right? And what we said is that the stack is just going to store a list of tuples or lists, right? Of, I guess it'll make more sense if we do it like this: list of element and min at time of addition, right? And so this is what we have: minimum, the element that we're adding, and the minimum at the time of the addition of this element, right? So which one is smaller, the new element that we're adding or the previous element but the minimum at that element's time of addition, which would be the second value in the list, right? So we can take that away, and we're removing, right, now that these values are stored in the same spot, we can just do self.pop, right? But we also have to make sense, right, because we're storing this as a list of lists, right, or a list of tuples. I'm just saying list of tuples because you can do that in other languages, but you can do this in Python too, but this is just a list of lists. So we're going to say self.stack.pop, but stack stores 2 items, right, per element, right? So we have to return the 0th element, right, which is just going to be the element that the actual value, right? And then when we do top, we're going to look at the last element, right, but the last element in the stack, but the first value in there, right, which is going to be the element we added to the stack. When we say get min, we're going to say return self.stack, the last element, but the first, or I guess the second element in the list, which is going to be the minimum at that time. And this should work as well. I forgot to remove this. And this is the same thing. So, so what's the time complexity, right? Well, obviously, we implemented all of these to be constant time. So this is constant time. It really depends on how the underlying arrays defined here, because we're just using a Python list. But usually insertion in an array is constant time amortized. But or adding to the end, at least the way we're using it. And so the space here is going to be linear space, because if we're adding n elements, right, we're going to store n elements, right? I mean, you could argue that for each element, right, that we store, we have to store another value, assuming that they only add ints to this list. So it would be like 2n or something. but 2n is the same as n, so it's just linear space. So that is 155 min stack.